So today we have Dr. Bin Chen with his presentation about solar flares with Jansky Very Large Array. Bin is an associate professor at the Center for Solar Terrestrial Research at the New Jersey Institute of Technology. Prior to that, he held an appointment as astrophysicist in the Howard-Smithsonian Center for Astrophysics and a postdoctoral fellow at NJIT. He obtained a PhD in astronomy from the University of Virginia in 2013, and he was recipient of the NSF Career Award in 2017 and the NASA Living with the Star Jack Eddy postdoctoral fellowship in 2013. The Chen's research focuses on solar high-energy phenomena associated with explosive events such as solar flares and coronal mass ejections by using radio and multi-wavelength observation. He is a core member at NJIT's Solar Dedicated Radio Observatory, the expanded Owens Valley Solar Array. He also utilizes some of the world's premier general-purpose radio facilities for solar studies, which include Jansky Very Large Array and Atacama Large Millimeter Submillimeter Array, ALMA. So please go ahead. You have 45 minutes and then discussion questions.
Great. Thank you, Gregory, for the introduction and for inviting me here to give the talk on April the 1st. That's a special day. First of all, I hope everyone doing well during this global crisis. But let's have a little bit of fun. So I changed my title of my talk to Searching for Aliens with the Carl-G. Jansky Very Large Array. So I stole Jodie Foster's poster and Carl Sagan's name. But yes, my real title is Solar Flare Observations with the Jansky Very Large Array. So this is not just my work, it's the work, a collaborative work with a lot of people, including all those folks listed down here, NJIT, NIL, CFA, Minnesota, the Switzerland Friends, and our Air Force Research Lab and Nagoya University. So the title is, I'm going to focus on the works we have done with the Jansky Very Large Array. We're also doing a lot of work with NJIT's expanded Owens Valley Solar Array. So hopefully in the future, someone from our group and already people from our group like Dale Gary has already introduced, and also Jelu introduced observations from the EOFSA. Okay, so as usual, just to motivate the study, this is a recent observation of the 2017 September 10 X 8.2 class flare. And this flare looks very nice in terms of its perfect viewing geometry, which represent really nicely the so-called standard flare CME model as depicted on the right. So this is a cartoon from Jin Ling and Terry Phopps, 2000. So the eruption can be seen, okay, as the erupting flux flow going upward. Maybe I didn't change color. So this is the flux stroke viewed along its axis. So the eruption of the flux stroke will induce current sheet following the flux stroke over here, where the magnetic field at both sides of the current sheets has antiparallel polarity. So at the center, it induces strong current, which facilitate the so-called magnetic reconnection. So the reconnected flux, part of them add up into the flux stroke itself, and part of them going downward and form the so-called flare arcades. And the flare arcade is visible as the cusp-shaped loops, as you see from the movie on the left. So if we focus on the flare site, so this is another cartoon adopted elsewhere. Interesting. Looks like on the screen is something funny going on. Okay, now it's good. So if we focus here, we have reconnection outflows. When the reconnection outflow hit the loop top, it may or may not form a shot, which we're going to discuss a little bit. And then a loop top hard action source will appear at the loop top, and the electrons, the accelerated electrons, can go downward and hit the chromosphere, and of course the hard X-ray foot point emission via bremsstrahlung. And the high pressure, because of the energy dumped into the chromosphere, can force hot material to go up and subsequently fill up the fluorite, which is visible as the soft X-ray and EUV hot loops, as you see from the observations. So hot X-ray foot point over here, soft X-ray arcade with hot X-ray loop top source. So this is the current picture of the standard flare model and the subsequent emissions. And we also speculate that reconnection site is not just one single X point. It could be a spatial distribution of many reconnection sites, possibly look like this. So if we zoom in on a particular X point, it may have a lot of either magnetic islands or turbulence. So we just call it fragmentation. If you further zoom in, there are many other smaller scale magnetic islands. This is just to facilitate the energy release during reconnection. Okay, so that's basically the current picture, but we had this lot of unknowns, although it got the name of a standard model. So some of the outstanding questions include, well, where and how do magnetic reconnection and energy release occur? So in the cartoon, there's only one X point, but as I previously said, well, there could be many X points, and there could be a current sheet that's releasing the magnetic energy. There could be the cusp region is also doing the magnetic energy release, according to a recent paper by Fleischmann et al. 2020 in the Science magazine. So the second question relates to, well, there's a vast amount of energy released during the impulsive phase and later phases. That's originally magnetic energy. So we need to convert this magnetic energy into other forms of energy, including the energy in accelerated electrons and ions and thermal plasma and the bulk flow. So where and how does this energy conversion occur is also a outstanding question. So last one, what is the physical nature of the reconnection sites? And this is the last but not least, but we don't really know what's going on inside the reconnection sites, including what is the actual current density, what is the level of fragmentation, and what is the elementary size that determine the magnetic energy release, and what is the interplay between the reconnection, shock, and also turbulence in those sites. So we have included some relevant discussions in a recent white paper submitted to ASTRO 2020, the Gödel survey, and this is a link. By the way, all the slides will be uploaded to Gregory's website, so you can download a file afterwards, including the link if you're interested. Okay, so those outstanding questions, how do we address them? One of the method is via radio emission. So we observe radio emission in solar flares, and those radio emission produced by different sources and via a variety of emission processes. And all those processes, they have its own benefits. So some of the processes are can be used to diagnose thermal plasma, and some can provide diagnostics for energetic electrons, magnetic field, thermal plasma. So here, I'm going to focus mostly on this type of emission, coherent radiation. I'm going to discuss a little bit about gyromagnetic radiation. It's just because, well, the instrument, the very large array, is very suitable for detecting and analyzing the coherent radiation from solar flares. So in short, the coherent radiation, well, they can arise from a relatively small population of non-thermal electrons, as long as the condition for coherent radiation is met. So one of the most well-known coherent radiation mechanism is plasma radiation. So the plasma waves are generated in the form of mostly Lamian waves and sometimes upper hybrid waves. Those are longitudinal waves, so it needs some wave particle and wave conversion processes in order to convert into electromagnetic waves, which are radio waves in the solar corona, and then be observed. So one type of this kind of instability that generates the plasma waves, the Lamian waves, in the first place is the so-called beam instability. So if you have electron beam propagating along the field line, in addition to a distribution that's more or less Gaussian, but this is a velocity distribution, you have a little bump which represents the bulk velocity of the electron beam. This is measured at a particular time and particular space. Okay, so this actual bump will give rise to the so-called beam instability, which will generate the Lamian waves and rise exponentially until it saturates. And this high level of Lamian waves can be converted further into radio waves. That's one of the types. And the other type is the so-called electron cyclotron maser emission. This has something to do with the resonance between the plasma waves and the electron cyclotron motion. And one of the instability that gives rise to this bright coherent emission is a so-called loss cone instability. So at the boundary of the loss cone, so this is again an angular distribution of electrons. But inside the loss cone, so this is the loss cone. This is along the direction of the field line. Inside the loss cone, electrons get lost pretty quickly. And outside the loss cone, the electrons, they are there. So there's a boundary where you basically have a inversion of the particle distribution, which gives rise to the instability. So whatever that is, there are many types of coherent radio bursts, but by observing those emissions and resolve them spatially, temporally, and spectrally, we can learn a lot about, first of all, what is the property of the background plasma in which the electrons are propagating, and sometimes also the magnetic field of the source. It really depends on what kind of burst we're talking about. The thing is, we have a whole zone of the coherent radio bursts that we observed, which can serve as those potential diagnostics tools. So, well, there's so many mechanisms that's working, but what do we see? Well, I took a cartoon from Edward Kanta. So on the left, this is a simplified scenario of reconnection-driven emissions at radio wavelengths. So presumably electrons are accelerated somewhere over here. And electrons can escape along the open field lines outward, and those will be observed as the so-called interplanetary type 3 radio bursts. But also, the emissions can be generated from downward going electrons or trapped electrons somewhere in the flare region. producing coherent radio bursts or microwave gyrosynchrone radiation. So if we take a generalized picture of the so-called radio dynamic spectrum, this is the time axis, and this is the frequency axis in logarithm. The frequency is dropping as we go up. It's reversed from the usual sense because the higher the frequency, the emission usually comes from lower in the corona. Up there, frequency is smaller, but the height is also is larger. It's larger heights. So at the flare on site, we see really quickly frequency bursts with large frequency drift, which are the so-called type 3 radio bursts from the escaping electrons into the interplanetary space. Sometimes we also see type 2 radio bursts like this with a smaller drift rate. Those are from presumably coronal shocks in front of the CME or at the flank of the CME that's propagating outward. And those shocks can accelerate electrons, and the electrons can in turn go through a series of conversion from Lyman waves to electromagnetic waves. So that's the type 2s. And type 4s are usually regarded as a continuum, a bunch of emission in the frequency time space, and some of them are moving. They usually are regarded as trapped electrons either inside of the CME or behind the CME. So we have type 2, type 3, type 4, and there's something called type 1. So type 1 noise storm is something weird. And according to Stephen White, you don't really want to discuss it because of this little understanding about the type 1 radio storm. But observationally, type 1 storm is very common. It can be observed above solar active regions, usually for hours, sometimes days. But the origin of the type 1 storm is unclear. But apparently it's associated with some kind of energy release in quiescent, above quiescent active regions. So, and there is also type 5. I really don't want to get into that, but down here, where the frequency is higher or coronal height is low, we usually see microwave bursts. And generally, at the lower frequencies up there, it's usually dominated by coherent radio bursts. And at the lower heights, it's usually dominated by incoherent radio bursts. What I say is usually, but we should really analyze this in a case-by-case basis. So if you want to know a little bit more about a review about what kind of radio emission from solar flares, the review paper by Tim Bastian in 1998 is still a good reference. Okay, let's move on. So how to observe them? Well, we can take an antenna, observe the total intensity, and slice it in time and space, producing those radio dynamic spectrum. And if we do it nicely, it reveals a lot of substructures like this one. So this is a paper reported by Sam Toon, reporting a lot of type 3 radio bursts with flying structures. But although very interesting, and we can do this kind of observation at really high time and frequency resolution, it lacks spatial resolution. So the other way of doing this is take an interferometry and form an image using the technique of synthesis imaging and produce an image of the sun at given frequencies. So only until recently we can combine the two. This is something called radio dynamic imaging spectroscopy. wondering why keeping messing up. Okay, maybe WebEx. Okay, so if we combine the two, making dynamic spectroscopy, radio spectroscopy, with synthesis imaging at the same time, which means we have dynamic spectrum on the left, and any pixel on the dynamic spectrum, we can go ahead and pull out the visibilities observed by the interferometer and form a solar image. And this is the recent example put together by Sijie Yu, who is a colleague of us, with the very large array. So this basically gives us a lot of images at different times and frequencies. Another advantage of having this capability is that, well, we have basically a four-dimensional observation, two spatial axes, time and frequency. And also go ahead and go to the image cubes and call out, well, let's see, what is the time and frequency variation from this particular source, this particular location in the sky, and pull out the so-called spatially resolved radio dynamic spectrum. So this is an example from LOFA by Diana Mosan, 2015. So from this particular location, the type 3s, on top of the type 3s, we see a lot of so-called S-bursts. And if you want to pull out the time and frequency variation of this source, it's mostly all type 3s. This is another, on the right, there's another example from Jansky Very Large Array. This is during a M-class flare on 2012, March 10. And if we saw three distinctive sources, one over here, another one over here at the loop top, and third one hanging around over here. So if we draw a box around the source and obtain the intensity variation in time and frequency, we find out, well, the loop top source is mostly a continuum source, which likely have a gyrosynchrotron origin. And this source near one of the foot point or ribbon exhibit as pulsations. And this source hanging around in the corona, they exhibit as a lot of spikes. So I'll come back to this event and see, what kind of information we can get from there. But this just as a demonstration of, having observation in multiple dimensions. There are a lot of possible ways we can slice the data and get useful information from the data. So we call the vector dynamic spectra reveal intrinsic properties of very different radio sources, as you can see in the time and frequency domain, which should have different origins, and they appear at the same time. If you put this all together in the total power spectrum, you lose track of the different time and frequency properties. So that's a very good capability. Okay, so just a few words about the Very Large Array. It's a 27 element reconfigurable interferometric array. It usually has four major configurations, so-called A, B, C, D. So A is 36 kilometers down to D, 1 kilometer. And those two configurations are usually applicable for solar, just because of the baseline, the length of the baseline. And the VLA was first dedicated in 1980s, but it was upgraded in 2011 with hugely improved capabilities. So here is a table I pull out from Rick Purdy's introduction paper. So the legacy VLA is here, the Jansky VLA is over here. So there's a huge improvement in a lot of parameters. The one I like the most is the frequency coverage, which is over here. Frequency resolution, frequency channels, maximum bandwidth, and also the time resolution increased by a factor of up to 200. So the finest time resolution is only 5 milliseconds. So we can do really fast imaging and spectroscopy at the same time at really high cadence. So this is largely limited by the data rate. We are approaching the maximum data rate right now. So we are getting 300 megabits per second of data for the raw visibilities, which will convert into many, many images. The other thing I like a lot for the upgraded VLA or JetSki VLA is the time of scheduling in advance. Previously, we have to submit the proposal, okay, waiting for approval, and then you need to let the operators know 1 month in advance when you are going to run your observation. You really need a lot of luck in order to catch a flare. So for JetSki VLA, now we are allowed to tell the operator, okay, so there's an active region that's producing quite a few flares, and we can tell them, okay, let's do this in 1 or 2 days, tomorrow or the day after tomorrow. Can we do that? They will compare your priority with the others and see, okay, you can, or sometimes they tell you, no, you cannot. But anyway, you have this advantage of predicting whether you will get a better chance of getting flares or not. So that helped a lot in terms of catching flares in the previous years. So in terms of frequency coverage, now those bands are commissioned from P band to Ku band. So P band goes below 1 gigahertz all the way up to Ku band, 12 to 18 gigahertz. So those yellow blocks are commissioned for solar. So I'm not going into the details, but one thing I want to point out is that we can make really fast cadence images at 1,000 frequency channels at once, and that convert into more than 1 billion radio images per hour of observation at the maximum time frequency resolution. That's the orders of magnitude more than what AIA does today. Okay, so why JetSki VLA? Well, the frequency coverage of VLA is very nice to probe the heart of the energy release. And also the high frequency and temporal resolution is ideal for studying the rapidly varying coherent radio bursts. But it's not ideal for observing the broadband gyrosynchrotron radiation, which need a wide coverage. So that will lead to expanded Owens Valley solar array, which we expect to talk about this sometime later. So we have a bunch of observations made previously. So you can find a list available over here. We got more than 20 major flares. What I mean by major is larger than C class, and many, many micro flares. I will introduce some of the micro flare results. So if you're interested in proposing for VLA time, you can go to the NIL site for detailed instructions, or contact me if you want some help. So here I will briefly introduce some of the recent results, including tracing fast electron beams, mapping solar flare termination shocks, imaging waves and oscillations, and microflares. So I do this pretty quickly, just as overview of what we have done with the VLA and what can be possibly done with the VLA. And the potential is still out there. So a quick thing about type 3s, most of you already know, electrons going along field lines, they generate Lamian waves, and Lamian waves are converted into electromagnetic waves. And good thing about the electromagnetic waves, radio waves from the propagated electron beams is that they scale directly with, well, they are just 1 or 2 times the plasma frequency, which is a function of only the density in the environment. So if electron beam going up, the density is going down, and the frequency is also going down. So you will see a type 3 radio bursts with a frequency drift going to the lower frequencies. Electron beam going downward, density going up, frequency going up, and you will see the so-called reverse drift type 3s. So the frequency drift going to higher frequencies. So that's the simple picture. But the good thing about imaging spectroscopy is, what if you can make images out of each of the frequency? You can go back and check it to the flare site. So this way you can map out the trajectory of the electron beams, either going up or going down. So one of the example, okay, so this is the example showing that we just make a series images from high frequency to low frequency. You can see from the movie, the source originally is over here and then moved to there at the lower frequencies. And if you take the centroids of the radio emission, I should draw it the other way, but anyway, the centroids form from low height to higher height. The low height because we have a Bressi footpoint source at the base of the jet. So we can do this for one type 3 radio burst. We can also do this for many type 2 radio bursts. If with high resolution, time resolution, we can resolve those individual type 3 radio bursts with the VLA. So this is a recent work we have done for a group of type 3 radio bursts observed in a tiny microflare. So those are the group of type 3 radio bursts. And we separate this into two major groups, one group over here, another group over here. And each group is only a few seconds in duration. But we have observed with the 50 millisecond time resolution, we can map out the trajectory for each of the group. And interestingly, okay, so this is the same technique, make images at all frequencies. And this is a trajectory for one of the electron beam. So if you do the same for all the electron beams, it's supposed to be a movie. Okay, anyway, so one electron beam, you get this. Second electron beam, you get this. Third electron beam, all within the same group. So this is the trajectory colored in time for the same group. Also a lag. On the right panel, there's a trajectory for all the electron beams from the same group. And they all seem to come from the same site. We interpret as the magnetic reconnection site. Okay, so there's a lot of lag between what I'm seeing on the screen and showing on the WebEx. Anyway, so this way we can pinpoint the location of the magnetic reconnection. And the other interesting thing we find out is that, well, with this only 1 to 2 seconds of duration, there are many, more than 10 field lines, different field lines packed into a very compact region. So that's a clear indication of a temporal and spatial fragmentation in a tiny reconnection region, which we can pinpoint down to less than 1 megameter across. Okay. So Gregory, there's nothing advancing on the screen apparently. Are you guys still?
I see a page, a common origin of electron beams.
Yeah,
Electron beams from reconnection null points now.
Yeah, I have two screens. One is on my, presenter. Another one is what I see. So I'm okay. So now it is.
Okay, we have to.
Yeah, it's like a 2-minute delay of what I'm discussing and what is showing on the screen. Anyway, so the second example is to map solar flare termination shock. This is hard. So the termination shock forms when the high-speed reconnection outflow coming from the reconnection site it exceeds the local fast magnetosonic speed at the loop top and form a fast mode shock. So this shock has been suspected as one of the possible mechanisms for accelerating electrons, but observational evidence remain pretty elusive. Ooh, that's 2 minutes ago. Anyway, we observed a eruption on 2014. So this represents a classic erupting flare, but it's only a C1.9 class, so a rather weak flare. It's a long duration, and we see a lot of features, including erupting flux drop in AIA. We see a loop top radio and hard X-ray source. The more fascinating thing is that above the loop top, we see a bunch of fast plasma downflows. At the boundary of the downflows, we have a radio source, and using the vector dynamic spectrum technique we discussed before, by making a plot of the intensity of the loop top radio source as a function of time and frequency, we see this represents as a stochastic spike bursts. And I'll skip the emission mechanism, but it's probably due to plasma radiation. So the good thing about this is at the surface of the termination shock, we can have fluctuations with different kind of density. So different kind of density, you will have different kind of emission at different frequencies. So if you make one image at one given frequency and take the centroid, it represents the centroid of one of the density fluctuations. But if you make images in many, many frequencies, so it can help to map out the centroid from different frequencies or different densities. So if we place them together, it outlines the termination shock surface. So this is basically what we have done. And one thing we find out is that during the disruption of the shock surface, which you are not seeing on the screen, there is a reduction of both radio and hot X-ray flux, which we interpret as, the absence of the termination shock will lead to a less efficient electron acceleration, so that we have a smaller amount of non-thermal radio and hot X-ray emission. So recently we have reanalyzed this event. So one thing we find interesting is that if we look at the dynamic spectrum in detail, apparently you can separate the dynamic the spike burst into two groups. One form a lane at high frequencies, another one at low frequencies. So if we make the centroids, so the low frequency ones, the red ones, are statistically higher in height than the high frequency ones. And we know this statistically because we measure the heights and put them into the histogram, and the difference between the heights are skewed largely to the negative side, means the high frequency ones are located lower than the high frequency lane, low frequency lane. So our interpretation is that, okay, so those may represent the emission from the upstream. So this is the upstream, different color, upstream, and this is downstream. The separation is only about 1 megameters, so it's okay for the scenario of emission at the upstream and downstream. But more importantly, the frequency ratio, so frequency ratio F downstream over F upstream is proportional to square root of number density downstream to number density upstream. And that basically gives us a density compression ratio. From the interpretation and the measurement, we found out the shock compression ratio is about 1.5 to 2, which turns out to be, well, if we assume hydrodynamic shocks, then it's about Mach number 1.5. So this is very similar to the coronal shocks that generates the type 2 radio bursts that's propagating, okay? And for those type 2 radio bursts propagating coronal shocks, sometimes we also see the so-called band splitting or split band features. And the compression ratio and Mach number are also comparable. So this is another piece of evidence that suggests a weak shock also at the flare arcade that may be associated with the termination shock. Okay, so my student Injie Luo and I were working on the other event that we introduced earlier that we see in the coronal region. We see some kind of spike burst similar to what we observed before in 2012.
Ben,
Yeah,
you have 5 more minutes.
okay. So we did some three-dimensional reconstruction of the location, and we find out this is likely located again above the loop top because we have observation from both SDO and stereo. So stay tuned. We'll summarizing the results into a paper. So let's move on to waves and oscillations. So that was a nice result by Sijie Yu, who observed a radio source near the flare ribbon. So the radio source in the diamond spectrum is peculiar because first of all, it moves downward, which means going into high frequency or lower height, and then it moves up. So again, we can make images for those radio bursts. And what we found is that, well, as a function of time, it starts from here, higher height, and then move down as you go to higher frequencies, and then move up again. So this is like a reflective emission in radio. And we find that the propagation speed in projection is about 1,000 to 2,000 kilometers per second, which is typical for aphanic or fast mode MHD waves. They sort of bounce back and forth near the flare ribbon for some reason, which I'm not going to discuss in detail. Another thing we find interesting is that if we look at the lengths in detail, we find some oscillation patterns in the intensity, which we interpret as basically a packet of MHD wave going downward with its intrinsic more faster periods. So we analyze the energy carried by those waves, and we reach a conclusion that at least for that time, the estimated energy flux carried by those wave packets is comparable to those suggested by the ribbon brightening at the same time, as seen in UV AIA 1600 emission. Okay, the last 1 or 2 minutes. So we're also working with our colleagues in Switzerland, Marina Battaglia and Rohit Sharma, on some VLA observations of microflares. And this is an interesting result. So one thing I would like to point out is that VLA has the sensitivity to observe a lot of radio bursts, even from weak microflares. So this is a period that we had the observation. You can see from the ghost light curve, it's kind of flat, although it has a sea level, but there's really not much going on. But if we pull out the VLA observations, well, first of all, RESI shows a lot of smaller spikes, okay? And in radio, the emission is like everywhere. Some of the hard X-ray spikes has correspondence with radio emission, like this one, which is very nice. Those are either type 3 light bursts or broadband emission. And some of them seem to have a lack of radio emission. So the event itself is fascinating. Marina made X-ray images for different peaks. So the X-ray source is switching between different sources from east to west. And the radio waves preliminary analysis suggests that, well, it doesn't have any one-to-one spatial correspondence between the X-ray source and the radio source. So radio source is mostly sitting in between. So we are having a more detailed analysis on this event. So hopefully we'll be updating you guys later. So last slide. So this is another paper almost finished by Rohit Sharma. So this is also radio bursts observed in a low B class micro flare. The flare class is about B1.6 after background subtraction. And even for this kind of tiny micro flare, we can see two ribbons. A radio emission near the foot point, one of the ribbon, and the high energy, the blue one, is also near one of the northern ribbon. And there's a lower energy X-ray source that represent a flare arcade. So for this radio emission, we think they may be associated with the gyrosynchrone emission. So this is a rising spectrum in the optically thick side. And we fit a magnetic field of about 100 Gauss. For this tiny active region, it should be located very low near the foot point. Okay, so just to quickly summarize, there's an exciting opportunity provided by the new instruments that provide broadband radio imaging spectroscopy. And the examples I discussed is just a small set of possible science we can do with the Jansky Verilage array, and there are many more to be explored. And I should have to mention, expanded Owens-Vitey solar array is providing a totally different window that probes the microwave gyrosynchrone emission. Okay, so I will add a plug for Freezer, but as I'm approaching the end of the presentation, so I stop here.
Okay, thank you, Ben. It was a very interesting summary, and we are now open for comments, questions, and discussion. So please unmute your microphone. I'm closely monitoring. So, Angelos, do you have a question?
Yeah, I had one.
Go ahead.
I had several, but I was wondering about the accuracy of those centroids, because the radio observations are quite wide in spatial extent, the imaging that you're doing, but then you're presenting centroids. So how accurate are those when you're talking about such a small scale structures,
Yeah, that's an excellent question. So we have been using the centroiding technique for a while. So one of the assumption that goes into the centroiding is that, first of all, those are coherent radio bursts. So presumably, those are really unresolved point-like sources at each time and frequency. So in this case, the observed image is mostly, you can represent the centroid of the image as the source location pretty nicely. And the centroid accuracy scales with the beam size divided by the signal to noise or dynamic range of the image in the ideal case. But there's two things going in. First of all, we assume this is a point-like source, which is mostly, valid for the coherent emission. And second is that, well, we know the corona is scattering the emission around. So does the scattering contribute to, first of all, shifting the centroids? Luckily, at this frequency, above 1 gigahertz, the scattering is not as big as an issue as the scattering or refraction at the lower frequencies. So both of the two are have been considered. And the conclusion is that, yes, we can represent the radio source using the centroids pretty nicely. One of the way of seeing this is like the trajectory that we mapped for the electron beams.
Yeah.
They have a narrow, extension. So that sort of gives us confidence.
Okay, Hugh, your question?
It's about termination shocks. I also have a question about cartoons, but I can save that for later. So the termination shocks are kind of a direct prediction of the cartoon, right? The outflow of the reflection side, says there should be a termination shock in every flare, but it has taken a long time for this observation to happen. I saw the original papers by Henry Arras and Mann and others and didn't believe them. Your results are very believable, and I'm just wondering what you think about the difficulty of observing this. Is it really just the increased sensitivity of something like the Jansky VLA that lets you see them?
That's a really good question. So for sure, I don't have a clear answer, but I can throw some speculations out there. So in my 2019 paper, I sort of gave a better or more comprehensive review of what have been observed and my speculations about why we don't see those termination shocks often. Well, the one speculation I have is, first of all, the environment there is really complex. The loop top source is a region where it's constantly getting disturbed by the recognition outflows and all that. So in thermal, well, if we look at EUV and soft X-ray, it's really hard to see because it's get obscured by all those structures. Non-thermal, is a better probe in my, personal view, because these other structures do not contribute too much to the emission, especially those coherent radio emission. Is only sensitive to the site where the conditions are met, and so it's preferable in the vicinity of the shock surface. So that may be one of the reasons that coherent radio bursts like the spikes may be a good probe for the termination shocks. And the Ores and Mann et al., previously they had some imaging and spectroscopy, but perhaps not at the high resolution and centroid accuracy as we are doing right now over here, partly because the frequency they are using. Another one is, just the instrument. The other thing is, well, do those termination shocks form in every flares? So do they exist in the first place? It really depends on whether the outflow speed would be larger than the local magnetosonic speed at the loop top. If they're not, then we don't expect a termination shock. In fact, I have been working with Chen-Tsai Shen, an excellent modeler. So in his model, sometimes he has a termination shock, sometimes he doesn't, even in the same flare. So it's really, depends on, how the parameters come into place to form the shock, at least from the modeling point of view. I hope that answers part of your question, Hugh.
Yeah, thanks.
Okay, do we have any more questions or comments so far? I don't see any opened microphone.
I'll ask about cartoons then, if there's...
Nicole.
Okay.
Okay.
Nicole, go ahead, yeah. Nicole, you are muted.
Can you hear me now?
Yeah, go ahead, please, yeah.
Okay, yeah. So I had also a comment on the termination shock. And I agree with you when we first heard the results from Henry Arras and Gottfried Mann. We did not really believe what they were talking about. But I think that with the VLA observations, it's much more convincing. Then now I have a question about the slide that you show, the new results that you presented, where you measure the shock compression ratio. of the termination shock, which is relatively small. I was wondering, you observe indeed radio emission spikes or at the location which is close to the termination shock that in fact is seen in UV or UV, if I understand correctly. So, I mean, okay, there are some non-thermal electron acceleration there, but are we sure that the mechanism is due to the shock, or can it be due to some turbulence or some, I don't know, reconnection processes which are in the region close to the shock?
That's excellent question. So we don't know this for sure. I can just say that our interpretation now is that the termination shock fit most of the observation, evidence. But again, we cannot be sure that this is really due to the emission at the termination shock itself, because ideally, what really defines a shock is a jump condition. So if you can see, say, a velocity jump across the shock front, and here we presented, a density jump across the shock. But if there's other evidence that support that, that would be excellent. So that comes back to your first part of the question about UV. So this kind of density compression, in principle, will give us a UV DEM emission measure difference of a factor of 3 to 4, which can in principle be observed in AIA. So we had dedicated a section of the discussion in our 2019 paper. We found out, we didn't see such kind of EM change across the shock front. Part of the reason, I suppose, is the termination shock front, the surface, it shouldn't have a long extension along the line of sight. Maybe only part of the current sheet, bottom of the current sheet, has the condition for generating a termination shock. So this compression enhancement is more likely to be washed out if you integrate along the line of sight. So that's our interpretation. But again, we are presenting observations, we are throwing out our interpretation, but any other interpretation we totally welcome. So it's up for debate, but that's what I mean.
Okay, thank you.
Yeah.
Okay, thank you. We have time for maybe 1 or 2 questions if anything available. So I don't see any open microphone, so every microphone.
I have a question that may also be the same as Hugh's about the cartoons.
Okay.
About the cartoons, the 2 cartoons you saw that are not consistent with each other, of course, the eruptive flare with the other one, type 3 from Edward Cornbutt. And
Right.
I want to ask these sort of beams that you were talking about early on. I mean, the first example about the beams. Are they always related to this sort of jets and not Flaxdrop like eruptions? Do you see them only there?
That's an excellent question. So we know, especially for the interplanetary type 3s, we need open field lines that open to a large radius. So that either require if Fluxdrop is involved, then the Fluxdrop need to open up the field line, or as you said, the jet, it has a natural, opening to the interplanetary space. So yes, the 2 cartoons are not consistent with each other, but maybe just the standard flare is really for a flare model is really for the erupted flares, but not for the jets. So yeah, it could be just different geometry involved in the reconnection.
But from the events that you have, those 6, 7, or so dozen events, when you see those beams tend to be jets, or do you also have CME-like events in there?
That's a good question. So, well, the events we have analyzed so far do not give us good statistics. But for the few events we analyzed, jets are, all of them are associated with jets, like 2, 3
Okay.
events.
That's very good.
Yeah.
That's very good. Yeah.
But not statistically significant, so don't quote me.
Yes. Okay. It's okay. We'll talk about we'll talk this offline more later. Thank you.
Yeah.
Okay, thanks, Ben. Thank Angela. I have couple words about the webinar. So next one will happen as usual in 4 weeks from now. Cassie Reeves will be talking about X-ray corona. As of May, the event will change its format and change as a time. So stay tuned and follow announcement in the Solar News. So see you in next events. Thank you very much. Thanks, Ben. Bye-bye.
Thank you so much, Gregory. Thank you, everyone. Stay safe.